Hello everybody, welcome back to another video, and today we're going to be talking about the powerful U-substitution. So this U-substitution, what we're really looking for in an integral when we want to use this is specifically when we're looking at long complicated expressions with a lot of fluff in them that we can break down or simplify as we replace the variable x with u and get rid of some of those x's and just try to consolidate everything down and make it easier for us. And this can also help us, turn the integral into something that we know how to integrate. So let's look at this first integral, the integral of 2x over 3x squared plus 4 to the 3 halves. So there's a lot of mess going on here, but one thing that I do like to see is we have a 2x and then a 3x squared plus 4. So likely we're going to be making a substitution involving one of these. So one of the things you want to look for is your inside functions. Look at your inside functions. Sometimes the inside function, especially at the bottom of the fraction bar, are usually the derivatives or similar to the derivatives of the top of the function. So when we're looking at this, the derivative of the inside of the bottom, inside that to the 3 halves power, we have a 6x. So that's one sign, and you'll see later how this pattern kind of comes along and how you can kind of, have an intuition for it. But it comes way easier the more problems you do. So the first step in these kind of problems is to let u equal to. Now, usually you want to do the more long and complicated expression in the problem. Not all problems are like that, but usually it's a safe bet to go for, in this case, 3x squared plus 4. So now we just redefine 3x squared plus 4 as the variable u. And you think that maybe we can just plug it in now. We can now just put in u. But the problem is we still have that 2x on top, and we're also taking the integral with respect to x, not u. So it's not actually going to take the integral properly if we don't change that dx to a du. So the way to change what we have right now as a u to du is to simply take the derivative of it. So du is going to be the derivative of u, which is 6x dx. Remember your implicit differentiation, of course. So now we're looking at this, and we currently have a dx in the equation. We want to replace that with a du. So we need to find dx in terms of du. And the way to do that is we can divide both sides by 6x. So now all we have left is we have 1 dx is equal to du over 6x. So now if we look at our new integral, we have integral of 2x divided by, instead of 3x squared plus 4, we're going to put u to the 3 halves, and then we're going to multiply, instead of by dx, we're going to multiply by du over 6x. So now, as you can see, we have an x and an x canceling here in the problem. So now that gets rid of all of the x's. So now all we're left with is 1/3 of, I guess technically 2/3 the integral of 1 over u to the 3 halves du. So basically we took the numbers out, right, of course, and actually that should be 1/3. There we go. we took all the numbers out, and now we only have it in terms of u. So now we actually can integrate. So now instead of this whole 2x and then 3x plus 3x squared plus 4 stuff, we now just have a 1 and we just have a u to the 3 halves, which we know how to integrate. You simply just use the power rule. So it's going to be, it's going to be 1/3 times 2 or -2, sorry, -2 u to the -1/2. So the final answer, or supposedly the final answer, is -2 over 3 root u. So our answer does not ask for this specifically. Our original integral, if you look up here, asks us this function with respect to x. So now we have to do is we have to reference our u substitution that we made earlier and simply plug back in 3x squared plus 4 for u. So now all you need to do is literally swap, and you just need to swap out that u. So this is going to be equal to -2 over 3 square root. And instead of u, we'll put 3x squared minus 4. And you can't forget to add plus c, and that's your final answer for this problem. So see, we went from this kind of complicated expression with a lot of fluff into 1 over u to the 3 halves, which is super easy. We can just take the integral of that right away. So that's why I said earlier one of the patterns you want to see is that the degree on the bottom is 1 degree higher than what's on the top. So that's how you get this little cancellation that happens. And there's a super tricky cancellation, and this cancellation is kind of what separates a difficult u-sub problem from like an easier one like this. So if we go down here, we have the integral of tangent to the 5th x, secant to the 3rd x, dx. I'm going to give you a moment to see maybe what can we do and what can we sub, or what are some ideas we have regarding this integral. Okay, so for this integral, we have a tangent to the 5th, which we don't normally see, and a secant to the 3rd, which we also don't normally see. So usually we're going to try to break things down into things that we know and that we can manipulate easily. So things that we can manipulate easily would be like a tangent, a secant, but also a tangent squared, a secant squared, and also think about trig identities as well when you're looking at trig integrals as well. And remember, tangent and secant are related to each other. Tangent squared is 1 minus secant squared, and of course, you know, the other way around. And so that's something that we can use to our advantage in this particular problem. So let's break down this integral into little parts. So in this case, we have a tangent to the 5th. Now, if this was like tangent to the 4th, maybe we could do like tangent squared, and then we can do something with that tangent squared in the inside. But we have a tangent to the 5th, so we'll have 1 left over. And the same thing with that secant to the 3rd, we're going to have an additional secant left over if we use the secant squared. So we're just going to have to try it and see how it goes. So here we have tangent squared x squared, so that's 4 tangents total, times secant squared x. So these are things that we can actually work with. And then we still have our leftover secant x, tangent x, and then we still have our dx originally. So now let's try to worry about this part that we had kind of simplified down. So what we can use is we can use our trig identities. So this tangent squared is the same thing as 1 minus secant squared. Squared times secant squared x times secant x times tangent x dx. Of course. And so now we have 3 secant terms and we have 1 tangent term, and we can't really do too much with that secant and tangent. However, because we have a lot of secant terms, let's see if something works out with U-subbing for secant. So a lot of times it's just trial and error to know what to U-sub, but in this case we're going to do U equals secant x. It seems like a pretty good choice. And if you think about what you're going to U-sub, we need to also think about the derivative. So the derivative du is equal to secant x tangent x dx. And so if you think about the derivative, you can think about what could possibly cancel out the bad terms. The bad terms are these two terms right here. These are the two bad terms that we don't like. These are the terms that we're able to work with, but the ones highlighted in green, those are kind of our just like leftover pieces that we really don't want in the problem. So in this case, this works out super well because du is equal to secant x tangent x dx, which happens to be all of our leftovers. So now you can literally just replace everything in green with du. So we have 1 minus, remember we define u as secant x, so now we have a u squared, and then that's squared, times, now we have a secant squared, so that's a secant squared on the outside, so u squared. And then instead of all this fluff with secant x tan x dx, we can just write du. So that helps us skip so many steps now, because now we just have a polynomial. We don't have to deal with these messy trig functions and these high powers anymore. So now that's all that's needed to do is you simply multiply this out. I guess there's probably other ways you could do this, but I'd say the easiest way is just to multiply it out. And you'd get u to the 6 minus 2u to the 4th plus u squared du. Okay, and after that, you just simply take the integral, because now we just have variables. We don't have any fluff going on, and we just have like easy power rule type stuff. So let's take that integral. So we have 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u to the 3rd. And remember, our original problem asks for respect to x, so we need to plug back in secant x for u. So remember, we made that u equals secant x substitution, so now we need to plug it back in. 1/7 secant to the 7th x minus 2/5 secant to the 5th x plus 1/3 secant to the 3rd x. And you always can't forget plus c, and that is our answer right here. We just went from this complicated long expression. We found the perfect substitution to cancel out all of the fluff and all the leftovers we didn't want, and we just made it simply a power rule problem where we just simply go through those motions, right? Nothing too complicated there. So it's all about simplifying that down to that easier problem. Anyway, I hope you liked this video, and I will see you all later. Goodbye, everyone.